And so in the last video, we were talking about the scientific method and the story. This is kind of a storyline. And so we're going to pick right up where we left off. Because you see, John Dalton, who by the way was an English man and a school teacher and a scientist, and a school teacher, so I like the guy, found some of Democritus' old works. Now how he found that, I'm not exactly sure. Obviously, it was through text and through written materials, but he came across some of Democritus' old ideas from 400 BC. Remember, we said at the time, for 400 BC, Democritus' ideas was very, very good. He talked about the idea of a small particle, which he named the atom. And Democritus said that the properties a certain material or substance had was a direct correlation to the type and the number of atoms that were, compiled together. Of course, he didn't understand about chemical bonds or anything like that. And so Democritus said the arrangement of atoms and the type of atoms cause substances to have different physical and chemical properties. Obviously, we know that to be true today, but for 400 BC, with no books, no colleagues, no lab equipment, just philosophical thinking and reasoning, that's remarkable. Well, fast forward to the year 1803, and this Englishman, this teacher John Dalton, expounded on Democritus' works using the scientific method. Remember, the scientific method at this point was relatively new, but it got rid of bias that was unfortunately, injected in science for so long, or persecution, however you want to term it, right? And so with this new scientific method, along with some new lab equipment and some studies and research from the scientific method and some friends and some colleagues he could discuss this with, John Dalton expounded upon Democritus' works, and he created what we now know as the modern atomic theory. All right? So I've already said all of this. So he proposed the first modern atomic theory. And for this reason, John Dalton is known as the father of modern atomic theory. And you need to know that for a quiz and for a test. Okay? Now, what we're going to do is we're going to take a look at 5 postulates that formed John Dalton's modern atomic theory. But you've got to understand this in context. Because you see, in the year 1803, the proton and the neutron and the electron had yet to be discovered. In fact, the first of those 3 particles to be discovered, the electron, was in 1897. So we still had 94 years to go before subatomic particles were discovered, right? So Dalton is just thinking about the atom in general terms. He didn't know that there were smaller particles that made it up. So Dalton's modern atomic theory, it's much more modern compared to 400 BC, has some flaws in it, in each postulate. So the following 5 slides are Dalton's conclusions of atomic theory, and the flaws will be projected in red after I read the theory. And again, we found that there were flaws to his theory once we discovered the 3 subatomic particles just under 100 years after that. Still not bad, though, for 1803. So John Dalton's first postulate in his modern atomic theory, he said matter is composed of small, indivisible particles called atoms. Now, that's absolutely true, right? Even Democritus said that atoms were indivisible, right? You can't just take a butter knife and cut an atom, right? So they're indivisible, they're small, absolutely. And this is true, but he didn't have the concept of those subatomic particles. The atom can be further broken down to protons, neutrons, and electrons, right? So, that's not bad for 1803. All right, he just didn't realize how small the atom really was, and that it had some other small particles helping it out, if you want to word it that way. All right, next in John Dalton's modern atomic theory, he said, atoms of a given element all have the same mass. They are identical in all respects, including chemical behavior. So, here's the deal. So that we're dealing with the element carbon. Yes, for the most part, all atoms of carbon do behave chemically similar. He's absolutely right. but they don't have the same mass. Not all atoms of carbon have the same mass. Not all atoms of hydrogen have the same mass. Not all atoms of oxygen have the same mass. And therefore they can't be identical in all respects because there's something causing atoms of a certain element to have different masses. And that is, again, one of those subatomic particles that won't be discovered for quite a while. And that is the neutron. So every atom, whether it be carbon, nitrogen, oxygen, hydrogen, you name it, can have different numbers of neutrons. So when an atom of the same element has a different number of neutrons, we call that an isotope. For example, you can have carbon-12 with 6 neutrons, carbon-13 with 7 neutrons, and carbon-14 with 8 neutrons. They're all carbon, so they do behave chemically similar, but they don't have the same mass, because every time you add a particle, you're adding mass. So therefore, not all atoms of the same element are identical. But again, that's not bad for 1803. John Dalton also postulated that atoms of different elements differ in mass. Now, he's saying the atoms of different elements this time. So he's saying that carbon has a different atomic mass than nitrogen. And he's right. So the atoms of different elements differ in mass. Absolutely true. And they all differ in chemical behavior. Now, 100% true, yes, they differ in mass. But differing in chemical behavior, not really, because you have to understand the periodic table has groups, right, and periods, columns and rows. The elements are arranged in specific ways based off their chemical properties. And the problem is, if an element is in the same group, like group 1, 2, 3, 4, 5, 6, 7, 8, don't worry, you'll learn about that quickly, they do have similar properties. And so they do have different masses. And yeah, they do all behave a little bit different chemically, but if they're in a similar group, the same group, they actually do to some extent have similar properties. But again, it's not bad. Dalton said in a chemical reaction, the atoms involved are rearranged, by the way, 100% true, separated, yes they can be, or recombined, yes they can be. So far, he is completely correct in what he's saying. And they form new substances in a chemical reaction. This is the part that he's not wrong, but he just didn't understand the full picture. He said no atom or no atoms are created or destroyed. Now, yes, he's right, but there's this thing called nuclear energy, right? You think about probably a nuclear weapon the second that I say that, but also realize it can be used for less destructive, not inhumane things, such as nuclear energy. And in a nuclear reaction, we're going to study those in the next video, you'll find that particularly in something called nuclear fission, you can take a really big atom, say uranium, you can bombard it with a neutron, and that atom will actually split into 2 new atoms. One atom will be krypton, and one atom will be barium. So you're not destroying the atom, but you are changing its number of protons, therefore changing it into a completely different element. So, it's not like the atom of uranium is totally destroyed and all of it's gone. It's just changed to a totally new element. And that's kind of on the verge of going against his atomic theory here when he's saying they're not created or destroyed. But hopefully you can kind of differentiate between those things, right? So he didn't understand fully the concept of nuclear energy. Well, because in 1803, as you'll see in the next video, radiation, nuclear energy, radioactive elements, and radioactivity, blah, 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 hadn't been discovered yet. All right? So those are Dalton's postulates in his modern atomic theory, which he drew from the work of John Dalton and enhanced using the newfound scientific method.